Hello, everyone. It's a pleasure today to present our speaker, Padre Bob Macke. He was a PhD in 2010 at the University of Central Florida, working on physical properties of meteorites. Then he did the master thesis on theology at the Boston College. And after that, he become part of the family of the Specula Vaticana, working on physical properties of meteorites. And just 1 year later on, he became the curator of the meteorite collection of the Specula Vaticana. So on 2020, he became part of the Osiris-Rex sample analysis team. And so he was one of the first to see the opening of the chamber and the capsula, and so to have the opportunity to see the samples from Osiris-Rex. And a part of his, we can say, scientific issues, another nice things to report is that he's working on a 3D models of the Sant'Ignazio Church with the observatory of Angelo Secchi, that was one of the Italian pioneers of astrophysics. So the floor is yours, Bob.
Okay, thank you very much. Thank you for that introduction. I'm very happy to be here. This is a great opportunity. Let's advance. Okay, so I am going to talk a little bit on the research that I'm doing at the Vatican Observatory with meteorites and studying their physical properties, and a few interesting results that we've had. And then I will also discuss some of the work that has been going on with OSIRIS-REx, in particular my research on density and porosity of the specimens. So when we talk about research on meteorites, I presume that most of you are somewhat familiar with meteorites, but just to be sure, meteorites are basically rocks from space, and most of them are asteroidal in origin. So in the early history of the solar system, you have the formation of large parent bodies, some of them differentiated into core mantle crust, some of them not differentiated. And then because of the chaotic dynamics of the early solar system, these things mostly broke apart and formed the asteroids. And then occasionally some asteroids find their way to the Earth, and we can collect them as meteorites. Here is one such object entering the atmosphere. This is over Chelyabinsk in 2013. You may remember that event. This is a piece of the meteorite in Vodili that fell in 2015, I think. And this was observed by the Desert Fireball Network in Australia. And so they actually tracked it coming in, and then they went out and found it and picked it up. There are very few meteorites that have been observed as bolides coming through the atmosphere and then collected afterwards. But when you have those events, the nice thing about them is that by tracking the bolide backwards, you can get a sense of where they're coming from in the solar system. And so here are some of the orbits. So you have some major axis and eccentricity. The dashed line there is the Earth crossing line. So only things that are to the left of that line actually intersect the Earth's orbit, which is why all of the dots, the dark dots, are the meteorites that have been recovered. The gray dots are just asteroids. But you notice that most of them fall very close to the line, because when they arrive at the Earth, the ones that survive to be collected as meteorites have relatively low delta V, so they're not coming in with incredibly high energies, so that gives them a better chance of survival. So we actually are selecting from when we study meteorites, we're selecting from a relatively small population of the asteroid belt. Now, of the meteorites we have, there are many different kinds. There are those that come from undifferentiated parent bodies, where you have the high density and the low density material all kind of mixed together. And in particular, you've got your chondrites, your carbonaceous chondrites, ordinary chondrites, and astatite chondrites, and I'm not going to get into all the differences just now because we don't have time, unfortunately. The name chondrite comes from the presence of chondrules, glassy melt droplets, that are basically something that formed in the early solar system and got incorporated into these things. But they have a mix of low density and high density materials, kind of mixed evenly throughout. So there's a lot of little metal blebs that you'll find embedded in there as well. Now you have from differentiated parent bodies, you have stuff that originated from the core of the parent body, iron meteorites, stuff that originated from somewhere in the core mantle boundary, pallasites, where you have the dense metals mixed in with medium density olivine. Some of those could be actually quite striking in their appearance. Some of them have olivine crystals that are quite large. And then the achondrites originate from the crusts. For instance, the meteorites that have connections with the crust of Vesta, the HED meteorites are an example of that. But we also have, curiously, also meteorites that originate from Mars, where you have a high energy event knocking material from the surface of Mars off into space, floats around for a couple of million years until it finds the orbit decays, eventually finds its way to the Earth. You also have meteorites that originate from the moon by a similar process. And then mesosideros, which I'm not going to talk about, but they're another stony iron meteorite, a mix of high density and medium density materials. Most of my research deals with chondrites. So a lot of my work has studied those because those can still contain a lot of the important signatures of the early formation of the solar system. By studying their physical properties, we hope to put constraints on formation models. So that's an important reason why we study the chondrites. And so these are the properties that I and my colleagues study. We study density, porosity, magnetic susceptibility, which is a good measure of the amount of iron that's in a material, and also thermal properties, heat capacity, thermal conductivity, coefficient of thermal expansion, things like that. So porosity, simply put, is a measure of the amount of pore space in the interior. And in order to measure porosity, the way that we do it is we actually measure two different volumes. So there's the bulk volume, which is simply the volume enclosed by the outer envelope of the material. And then there's the grain volume, which is the volume of the solid component of the material. And so, of course, the difference between those two is the void space. So the percentage difference is the porosity. And of course, because we like to use intrinsic rather than extrinsic properties, instead of expressing it as volumes, we express it in terms of their densities. So this one minus the bulk over the grain densities. Now, to measure the bulk and grain volumes, we need various techniques to do it. Bulk volume, remember, is the volume of the whole rock, the entire volume enclosed by the outer envelope. So what we used to do for this is we used a method of glass bead immersion. So you have a cup and you fill it, well, you put your specimen in the cup and you fill it with these glass beads that flow around it and fill all the extra space. And then using the average density of the beads, you can then calculate, by weighing the thing, you can calculate the volume displaced by your specimen. That's a fairly simple method. There are complications to it, but this, by the way, is actually a moon rock, an Apollo moon rock in that photo there. So I've applied the method on moon rocks as well. But one of the things is, with those glass beads, they get everywhere. They're messy. They're also not incredibly precise. So in more recent years, we've adopted a different method of using laser scanning, which is a fairly simple method. You use a laser scanner to create a shape model of your object, and then in the computer, you simply compute the volume of that shape model. And we switched, we adjusted the method because of the work with the moon rocks. So CapTem initially allowed us to measure a few specimens with the old method, but then later they got a little squeamish about it, and they said, are we absolutely sure that those beads are not contaminating in any way? And then they kind of said, you should use a different method. And folks at Johnson Space Center said, you know, we've got this laser lying around here. We haven't really used it much. Let's give it a try. And it turned out to work just fine. And ever since then, we've acquired a laser scanner at the Vatican Observatory, and you know, it is now the standard method that I use for measuring the bulk volumes and densities of materials. And so it has several advantages over the beads. One is no beads. Did I mention those beads get everywhere? It's been almost 10 years since we've switched. I still find beads in my laboratory. They just don't disappear. They get into little nooks and crannies everywhere. The laser doesn't make any physical contact other than photons with the specimen, which means you can work with very, very friable specimens. Like, for instance, the CI chondrite or gay, which if you look at it funny, it falls apart. But we've been able to do some great laser scans on this specimen and others like it. It does have a lot greater precision than the beads. We can really kind of get much better measurements with this method. And we can cover a greater range of sizes. The beads really work well for specimens that fit properly into a small range of cup sizes. If you try to get much bigger or try to go much smaller, it really skews the results quite a bit. But the laser can use the very same instrument on things ranging from a couple millimeters across to close to a meter across. And then in the end, you also have a computer model that you can do fun things with, including making 3D prints of it, which I've actually found the computer model has been quite useful in my job as curator, because I can use it as a negative when I want to create a support base for one of the display specimens, for instance. So here's an example of some of the sample size ranges we can work with here. So this is a piece of Almahata of a particular class. Almahata is a meteorite that has many different, it's very unusual. Each stone is practically a different meteorite type, because the asteroid that the stuff originated from was just a mix of a whole bunch of different things. This is a particular type that is underrepresented in the meteorites compared to what we think was in the asteroids. Very friable, and there was only a little tiny bit available to study. But Cyrena Goodrich wanted to know the density and the porosity of this specimen, and contacted me because she knew I would be able to get a good measure of it. But I mean, this thing is 66 milligrams. It's just a tiny little thing. It's only a few millimeters across. And on the other end of the scale, we've got this piece of Fukang, which is pallasite, that is 400 kilograms. And you know, it's the very same instrument was used to measure both of those. And this has allowed me to do some things like this study of the porosity as a function of the size of intact specimens of the Košice meteorite at Comenius University. So I used a laser scanner to scan several specimens ranging in size from less than a gram up to more than 2 kilograms. And measure their bulk volumes with the laser scanner, and then in combination with grain density, we're able to get their porosities and study the porosity as a function of these sample sizes. And we actually see that smaller specimens skew towards higher porosity, which makes sense because the more porous stuff is weaker and therefore would break up into smaller specimens, smaller pieces. And we just happen to see that in our sample here. So this is kind of preliminary work that we haven't really been able to crunch the numbers properly just yet, but it's still a very interesting result, and it's made possible because we have a system that can handle a large range of sample sizes. Now, in order to measure the grain density, the density of the solid component, we use ideal gas picnometry. And the basic idea here is you take your sample and you put it in a closed chamber and pressurize it with gas. We used to use helium, now we use nitrogen. So you measure the pressure, and the pressure times the volume stays constant. So you increase the volume by expanding into a larger chamber size. The pressure drops, and the pressure times volume initially, and the pressure times volume at the end is a constant, and then from that you can calculate the volume displaced by your specimen. And this is a method that has been widely used since the 90s, but has actually been used on meteorites and extraterrestrial samples since at least the Apollo program, because some of the early Apollo specimens had their density measured by this technique. And what we have at the Vatican Observatory is we have a commercial instrument made by Quantachrome that works great up to a certain sample size. And then I manufactured a larger instrument while I was studying theology at Boston College, because that's what you do when you study theology, right? And this second instrument can handle much larger samples. And in fact, what's in that picture there is hidden in the under the aluminum foil in the picture on the right is actually a moon rock. Is one of the Apollo moon rocks is in there. So to date, this technique has been applied on over 1,800 meteorites from many collections, our own at the Vatican Observatory, several institutional museum collections, several university collections, and also in our work, we're collaborating with a number of people at a number of other institutions. We do collaborations with the Desert Fireball Network in Australia. They'll find a meteorite and then they'll send it to us as part of their process of characterizing the specimen. George Flynn and Melissa Strayed and Dan Durda study hypervelocity impacts. So they actually used an ASAIMS vertical gun range, and they'll shoot a meteorite and measure its recoil. And an important part of understanding what's going on with the recoil factor is knowing the porosity of the specimen. So they asked me to measure the porosities of the pieces that they shoot. I mentioned the Alma-Hattusili studies, Slovak meteorite studies, I studied pore size distribution with John Friedrich and Alex Ruzicka, moon rocks and lunar meteorites with Walter Kiefer, and of course, more recently, the OSIRIS-REx sample return materials. Now, in addition to density and porosity, we also study magnetic susceptibility and thermal properties. Magnetic susceptibility is sort of a freebie for us because we measure it with this simple meter using geometric corrections that were established by Pierre Rochette and Jerome Gattacheka. And it takes 30 seconds to do the measurement, so we could just sort of do it alongside the density and porosity measurements. Thermal properties, Father Siopil, who's sitting right here, he has this fancy quantum design physical property measurement system that he's pointing at there, which can very precisely measure a number of different thermal properties at cryogenic temperatures, from cryogenic temperatures all the way up to 300 or 400 Kelvin. And so we've gotten a number of great data, and a lot of our more recent, most fruitful work has been through the use of this device with him. So a few interesting tidbits of some of our interesting findings here. One of the earliest stuff, so you may have seen this already if you've ever heard Brother Guy Consolmagno speak, is in studying the density and the magnetic susceptibility, we found that if you take the grain density and magnetic susceptibilities of ordinary chondrite falls, they group the three major types of ordinary chondrite falls, H, L, and LL, which is high iron, low iron, and low iron, low metallicity. If you use the combination of grain density and magnetic susceptibility, they group into three distinct groups, which makes this a fairly quick, fairly simple, and non-intrusive way to quickly classify these meteorite types. The work that I mentioned with the lunar meteorites, and I showed all those pictures of Apollo stones, they really, one of the fruits of that is we're able to compare the densities of the rocks with data from the GRAIL, the Lunar Reconnaissance Orbiter and such, and compare the gravity anomalies. And initially, they assumed in their work this, oh, I can't, nope, it's not. They initially assumed that the densities of the material, the crustal material is 2550 kilograms per cubic meter. We measured closer for similar materials from the Apollo collection. We measured 2700 kilograms per cubic meter, which adjusted the crustal thickness estimate for the Imbrium Basin by 25%. So, what's going on there? Okay. With the thermal properties stuff, we have other interesting results. Something, oh, gee, do it again. Sorry. Okay. As you can see here, this is the coefficient of thermal expansion for, on the left is CM carbonaceous chondrites, and on the right are lunar meteorites. The one on the right was just published this year. Oh. But at any rate, what we can see is with carbonaceous chondrites, there is a zone of negative thermal expansion that kind of peaks right around 235 Kelvin. And this is due to the abundance of phyllosilicates in these carbonaceous chondrites. With lunar meteorites, we have a zone of negative thermal expansion at much lower temperatures, kind of in the 50 to 100 Kelvin range. And that's due to the various silicates in the lunar rock. The curious thing is that there actually is negative thermal expansion to be observed at all. This is something you don't normally see in rocks. You usually just see it in pure minerals. And also that it's that you have two different zones for the two different for the CM chondrites and for the lunar meteorites. But it's also very curious. Lunar meteorites, they cover a wide range of different lithologies, but they all seem to have at least some negative thermal expansion, which is very curious. And this, by the way, comes from, there is a particular change in the vibrational modes as you cover certain temperature ranges. And so changing from longitudinal to translational vibrational modes goes from expanding modes to shrinking modes. And that's sort of what we're seeing going on in those cases. And it covers a certain temperature range and then goes back to longitudinal vibrations. Okay, so what you all came here for, Osiris Rex. So the OSIRIS-REx mission was a sample return mission, went to the asteroid 101955 Bennu, and retrieved a bunch of material from the surface and brought it back to the Earth. And why do you want to spend millions and millions of dollars doing sample return when you have all these meteorites to work with? Well, there's two things that you get from a sample return mission that you don't get from meteorites. And one is context. You know exactly where it came from. And in fact, the OSIRIS-REx mission, one of the things it did is it spent quite a bit of time orbiting Bennu, studying the surface. And so we got a lot of material about the asteroid surface itself from the orbit. And so now that we have material in the laboratory to study, we know where it came from, and we can compare the what we're finding in the laboratory with what we found from the spacecraft. Gives us more information. You also get pristinity. Meteorites, as soon as they enter the Earth's atmosphere, they're contaminated by the Earth's atmosphere. Particularly atmospheric moisture immediately starts to react with various minerals. If you have any organics, you get terrestrial contamination from terrestrial organics, and so you can't really study it very well. So by maintaining pristinity, you can study these things that you otherwise can't study in meteorites. Now, a few of the hypotheses that are important for me. One is that there's an abundance of magnesium-rich polysilicates. Now, that's not really important for the density and porosity, except when it comes to something you're about to see towards the end of the talk. But it was hypothesized from spacecraft observations that there's at least two distinct lithologies on the surface. And so it's an important part for our studies to see if we can distinguish at least two or more distinct lithologies among our return specimens. The material is going to be very porous, and the rocks themselves are going to be very porous, ranging from 25 to 55% porosity. This is based, again, on the spacecraft observations, with the different lithologies having different porosities. So the one type be lower porosity, one type higher porosity, which would be great. That means it's something we should be able to distinguish in the laboratory. And so by studying the density and porosities, we should be able to quickly distinguish diverse lithologies, which gives us a triage method before we send things off for the subsequent analysis. We can already have some sense of whether they're lithology A, lithology B, something else. And also hopefully to constrain the models of the asteroid structure and porosity, which I really haven't talked a lot about constraining models because I'm not a modeler. Other people use our data quite a lot. So at any rate, here's just a few nice little images of, on the right, upper right is a CG concept of the spacecraft coming in for approach with the TAG-SAM collection unit at the end of this long probe. On the left, the upper left, that's the collection unit, the TAG-SAM, actually touching the surface at the moment of collection. And then it was retrieved back to the spacecraft and put into this capsule that you see on the bottom part here. And that capsule was then sealed. And it was the capsule that returned to the Earth on September 24th of last year. And it landed in the Utah Test and Training Range in the United States and was immediately collected and transported to NASA's Johnson Space Center in Houston, Texas, where it was placed in a glove box. In fact, there are two glove boxes in this laboratory facility. One is for containing what's called the canister. So the capsule is the charred thing you see in the upper right that they're collecting. Inside the capsule is a canister, which is a sealed container. And inside the canister is the TAG-SAM collection head. So they have in the canister glove box, here you can see them opening the canister up. And you can see the tag SAM head right there at the bottom. And that was done at NASA Johnson Space Center. And this is a couple pictures of the tag SAM head. So this was when they first opened it up. This Mylar flap here had actually some stuff on top of it. They were not expecting to see stuff on top of this Mylar flap. They expected all the stuff to be on the inside. So they collected some of that, and then they tried to open up the whole thing, and there was a problem with some screws you might have heard about, which caused some delays. So initially what they did is they actually, they found out the Mylar flap was still flexible. So they actually kind of bent it back a little bit and were able to collect about 70 grams of material just from reaching in and collecting whatever they could find. So we were going to start the sample analysis with that material before we even got further. But then eventually, in January, they were able to manufacture a proper tool to open the stuck screws, and they opened up the tag SAM head. And so this is what they found, and that's just the leftover bits after they had already collected these 70 grams material. But there's a whole bunch of centimeter scale stones, both in this and also the stuff that already recovered, which is great for the kind of work that I do, because I work best with stones. With I can work with smaller powder stuff, but stones are best. Oh, and that's me kind of looking at one of the once things were sort of removed from the tag SAM head, they went into these little collection trays where they were then photographed and studied, and then we determined from those collection trays which specimens we actually wanted to collect for further studies. But yeah, I had a chance to actually see the stuff, which is great. And so one of the things is, because we wanted to do this triage work before stuff went to subsequent study, the sample analysis plan called for the measurement of density and porosity before we got to any subsequent allocations. And so that means that we needed to have instruments that were capable of operating under pristine conditions. Now, to do bulk density and volume, we use, instead of a laser scanner, we use a structured light scanning system, which is similar to a laser scanner, except it's sort of like a cross between laser and photogrammetry, because it projects a grid onto the surface of the specimen, and then takes photographs and does photogrammetry to recreate the shape model. And you can see the system there is on the outside of the window looking in, and the specimen is on the inside of the glove box, maintained under curation pristine conditions. But for grain density, we went back to ideal gas pyknometry, and this is actually why I was brought into the project, to develop the pyknometer for this thing. So the constraints that we needed for this ideal gas pyknometer were, first off, we needed the specimen and the part of the pyknometer that made contact with the specimen to be inside the glove box, so the specimen would never leave the glove box. But the electronics, which are kind of curation dirty, had to be on the outside, which means we had to have this kind of half and half system where half of the instrument was inside, half is outside the glove box. And so in order for that to work, it had to be able to fit through these 4-inch or 200 millimeter portals that were on the 100 millimeter portals on the side of the glove box. So we had to design around that constraint as well, which means it had to be able to slide in through this small hole, this 10 centimeter hole. We also were very limited on what kind of material. So anything that came in contact with the gas that was used in curation, or anything that came in contact with the specimen, had to be, and that's what I mean by wetted surfaces there, had to be a limited number of materials that were considered acceptable for curation. So certain types of aluminum, certain types of stainless steel, Teflon, Viton, and a small number of other approved materials. Nothing else. No, and also no lubricants, no oils, no, I mean, it's a lot of things were off limits on this. And for the gas source, because remember, ideal gas pygnometry uses an ideal gas, we used the same nitrogen that was used in the atmospheric feed for the glove box itself. So we're not adding anything to the system that wasn't already there. This is the design that I came up with. And as you can see, here we've got the sample chamber with the lid. Here's a complicated thing because it had to be operable by somebody wearing the gloves. So we had to design it so it was easy to operate. And also easy to reach from the other side of the glove box, because this glove box was probably not that wide. Too wide to reach across all the way from one side to the other. But this box here contains all of the valves and the electronic, the solenoids and the not all the electronics. In fact, the electronics were on a desk, but it contains all of the messy parts. And here's just I created this video in order to know all of the parts and pieces, because I actually had to do most of the design from here and order the parts in the United States because it was being assembled. Well, first the materials were being collected at the University of Arizona, and then they went to Johnson Space Center to be cleaned and assembled on site. And I had to know exactly everything that was in there and make sure that I knew it down to all the measurements and everything, and just every screw. I needed to know exactly how many screws of what kind. And so I created this Blender model just so that I knew that. And while I was at it, I figured I'd make this animation. And it's even better with the music, but I don't have that here. So the original design called it that to be wrapped in a Teflon bag, but that never happened. They decided it wasn't necessary. And there goes being inserted into the hole. And so a specimen goes into a foil liner and into a space filling cup that then gets inserted into the sample chamber. And that's one way. The foil liners were disposable. So that's one way to keep from cross-contaminating. And there's the thing actually assembled. And there it is installed. That's me kind of looking through the window. And that's in the canister glove box after they'd already opened up the canister and removed the tag SEM head. So there's a separate glove box for the tag SEM head once they had removed that. So it got moved over there. They cleaned up the canister, and then they installed the pyknometer in the canister glove box.